Question number 2. What is the magnitude and direction of the electric field at point P created by the source charges shown? The dashed triangle is an equilateral triangle with side length 3 centimeters. If a -4 nanocoulomb charge is placed at point P, what is the magnitude and direction of the electric force that the source charges shown create on it? Let's start by looking at the drawing. Because it's an equilateral triangle, we know that all these angles are 60 degrees and all the sides are 3 centimeters. And also because it's a 60 triangle, we know that we can bisect it along this angle and turn it into a 90, 60, 30 angle, which we can then use to perform trigonometry on it, which will come in handy later on. Let's start by thinking about what direction the electric field vectors will be. We know that an electric field vector created by a negative source charge is going to point directly towards that source charge. So we can draw that in there, and we know that an electric field vector created by a positive source charge is going to point directly away from it. And therefore we can guess that our resultant vector should be something like that. So, to start, we're going to find the magnitudes of each of these vectors, then break them up into their components, and then add them back together and find the magnitude and direction of the resultant vector, which we are going to call E3, E2, and E1. We know that the magnitude of an electric field created by a point source charge is equal to KE times the absolute value of the charge divided by the radius squared. So let's take a look at E1. We can see that the magnitude of E1 then equals 8.99 times 10 to the 9 newtons meters squared per coulomb times 6 times 10 to the -9 coulombs, all divided by 3 times 10 to the -2 meters squared. Now, performing the math on a calculator, we find that E1 is equal to 5.99 times 10 to the 4 newtons per coulomb. Now we want to find its x and y components. Looking at this, we can see that it is along the hypotenuse of the triangle. So therefore, we can use our trigonometric rules of y equals r sine theta and x equals r cosine theta to solve this. So in this case, E1 in the x direction equals the magnitude of E1, which is our r in this case, times cosine of 60 degrees, which in its turn is equal to about 2.10 times 10 to the 4th newtons per coulomb. Now we want to do the same thing with the y component. So E1y equals the magnitude of E1 times the sine of 60 degrees, because we've got the 60 there, and that is equal to about 5.19 times 10 to the 4 newtons per coulomb. Now we want to do the same thing to E2. The magnitude of E2 by this equation up here then is equal to 8.99 times 10 to the 9 times newtons times meters squared per coulomb times 8 times 10 to the -9 coulombs, all divided by 3 times 10 to the -2 meters squared, which, again, with our handy friend the calculator, gives us a value of 7.99 times 10 to the 4th newtons per coulomb. Now we want to do the same thing and break it into components, and we're going to do it exactly the same way as we did for E1. We have E2x equals magnitude of E2 times cosine 60 degrees, which is equal to that is equal to 3.1 newtons, times 10 to the 4 newtons per coulomb. We do the same thing with the y component. E2y equals the magnitude of E2 times the sine of 60 degrees, which in its turn equals 6.92 newtons per coulomb. Now we want to combine these. We look at our drawing and we see that our x's are both going to the left, so they're both negative, but we're only interested in the value, so I'm going to call them both positive. And they're both the same, so we just add them directly together to get the x component of E3. So E3x equals E1x plus E2x, which equals 6.99 newtons per coulomb. However, if you look at the y components, they're going in opposite directions. E2's y component is going up, whereas E1's is going down. So therefore, we're going to subtract E1's from E2's to get E3's. So E3y equals E2y minus E1y equals, that equals 1.73. Now we've got the components, but we need the magnitude. We can use because we've got the x and y components of this vector here, we're just going to call it that, we can use the Pythagorean identity of a squared plus b squared equals c squared. So we get that, therefore, the magnitude of E3 equals the square root of, I forgot the units there, of 6.99 newtons per coulomb squared plus 1.73 newtons per coulomb squared. And when you do that calculation, it works out to about 7.2 newtons per coulomb. So now we have the magnitude of our field. We want to find the direction of it too. If you look, again, if you draw a right triangle, I'm going to draw a better one here because that one's kind of sloppy, and we are going to draw it just like this. We've got our angle here. This is the angle we want to find for the direction. This is our y component. This is our x component. So we can just say that, therefore, theta tan theta equals y over x, just by looking at the drawing, opposite over adjacent, and then therefore theta equals the inverse tangent of y over x, and doing that gives us a value of 13.9 degrees. However, we're going this way, so it's actually 13.9 degrees above the negative x-axis. So therefore, we have our electric field, 7.2 newtons per coulomb at an angle of 13.9 degrees above the minus x-axis. Now, we want to figure out an electric, if we put, let me just erase this here, we have our little electric force. We want to find out what's happened if we put a minus 4 nanocoulomb charge there. We want to find the electric force. I'm going to erase the calculations up here because we don't need them anymore now that we have the answer down here. And I want more room to write. Now, we know, there, that's my negative x-axis, that's the theta, which is down here. Now, we know that the magnitude of an electric force equals the magnitude of the electric field times the test charge. So we know that the electric force equals, oops, this is supposed to have the times 10 to the 4. I just forgot to write that. So we have 7.2 times 10 to the 4th newtons per coulomb times minus 4 times 10 to the minus 9 coulombs, which gives us 2.88 times 10 to the minus newtons. Now that's the magnitude, but because it's negative, we know that it's in the opposite direction of the electric force. The opposite of the direction of the electric force is right here. We could do the whole same thing and find the vector components to find the angle, but there's a shortcut. We know that the x-axis goes like this. Right angle, complementary angles, it's the same as that angle, so we now know that this theta is 13.9 degrees below the positive x-axis. And that is the end of the problem. Thank you very much. How long was that?
Smiling bow. That was 11.